This training module on the VIIRS Active Fire Detection software is part of a training series on satellite products and tools for wildfire assessment. It was developed by the team listed here at the Geographic Information Network of Alaska, or GINA, which is part of the University of Alaska Fairbanks. NOAA algorithm developers Yvonne Caesar and Marina Sidulko provided valuable guidance and feedback. The basic outline of this training will include why the VIIRS Active Fire software is important, details about the VIIRS bands used by the algorithm, descriptions of the algorithm components, causes of false and missed detections, and methods to confirm the active fire's results. VIIRS fire detections are more important than ever as aircraft and other reconnaissance methods become increasingly expensive. This is especially true in Alaska with its huge and remote area of responsibility. With GINA's near real-time direct broadcast production, the reliability, resolution, and frequency of polar data in northern latitudes has made this software an essential tool for continuous monitoring of wildfire activity. For example, here are a couple of Alaska Interagency Coordination Center situation reports on June 14th and the 21st during the 2021 fire season. They show that VIIRS was the first indication of a fire and resources were being allocated because of it. The VIIRS Active Fire's output is delivered to the Alaska Fire Service from GINA via a GIS map server, where each point is accompanied with a table of information. On the left is an example plot of fire detections on GINA's Esri ArcGIS server with colors designating the age of the points for the Noatak fire in June of 2021. Red in a white circle, less than 12 hours, red in a black circle, 12 to 24 hours, blue, 24 to 48, and green is greater than 48. This fire was first identified by satellite, with resources committed based solely on those early detections. On the right is the Alaska Interagency Coordination Center dashboard with plotted points and the analyzed fire perimeter. Additional details about this and other fires are accessible from this dashboard. These animations of polar imagery show the fire evolution after those first early detections. The VIIRS I4 band, or 3.74 micron imagery on the left, is the primary input to the VIIRS Active Fire software, shown here with a special color map to enhance the hotter pixels associated with the Noatak fire. The red pixels in the Dayland Cloud Fire RGB on the right reflect the influence of the VIIRS I4 band. These animations show the growth of the Noatak River fire throughout the day, June 21st, 2021. Output from the Active Fires software includes the date and time, the fire pixel location, fire pixel brightness temperature, pixel resolution, a confidence value of low, medium, or high, and fire radiative power in microwatts, which is directly related to the biomass consumed per unit of time. A future version of the software for direct broadcast will also include persistent anomalies, which identify common sources of detections not related to wildfires, such as industrial sites, solar farms, volcanoes, etc. Note that the VIIRS Active Fire software also outputs a netcdf file. However, that will not be covered in this module. This table summarizes the satellite bands used in the VIIRS Active Fire's algorithm. The VIIRS I4 band, or 3.74 micron, is the primary band for fire detection, while the I5, or 11.5 micron, is secondary for detection and primary for cloud classification. The three reflectance bands outlined in green are used to filter for solar reflected energy that can generate strong signals in the I4 band during the day. Lastly, the M13, or 4.05 micron, is used in the fire radiative power calculations because it has a significantly higher saturation temperature than the I4. The low saturation temperature of the I4 can result in fold over with unrealistically cold brightness temperatures in the hottest pixels. The pixel IDs for these bands, outlined here in red, will be used in algorithm details later in this module. Here are some additional VIIRS channel characteristics. The 3.7 micron or I4 band is highly sensitive to fire emissions, but it is also sensitive to reflected solar energy. The graph on the lower right shows that the shortwave infrared bands used for fire detection lie between wavelengths that are primarily reflected solar energy and wavelengths that are primarily emitted radiation. As the upper right graph shows, the I4 band has a wide spectrum range from 3.55 to 3.93 micron. The sensor becomes saturated at temperatures around 367 degrees Kelvin or 94 degrees Celsius. The 11.5 I5 band is sensitive to emitted long-wave infrared radiation only, so it is not affected by reflected solar energy. The 0.64 I1 band is red visible wavelength with a strong solar reflectance signal. The 0.86 micron I2 has a strong solar reflectance characteristic from vegetation, and the 1.6 I3 snow and ice band has a strong absorption characteristic by snow and ice. The secondary 4.05 micron or M13 band is also highly sensitive to fire emissions and reflected solar energy, but at 750 meters, it is lower in resolution than the other I bands. The VIIRS Active Fires algorithm is quite complex, so this training will only touch on basic concepts. The algorithm is divided into several components, which are listed here, and for each pixel are processed in the numeric order shown. The first step in the algorithm process is to classify pixels as day or night, because the criteria will be different accordingly. Day-night classification is based on the solar zenith angle, where greater than 90 degrees is considered night. In the slides that follow, I'll get into more detail about each of the remaining algorithm components. After the day-night designation, the second algorithm component determines if the pixel is representing clouds or water. At night, brightness temperatures less than -8 degrees Celsius in the I5 band and less than 22 degrees C in the I4 band are designated as clouds. During the day, there are 3 brightness temperature thresholds for the I5 band depending on the reflectance values of the I1 and I2 bands. Note that pixels identified as clouds skip further fire detection processing. Also, it's important to keep in mind that no other algorithm component considers clouds. The daytime test for water pixels looks for a decrease in reflectances between the I1 and I2 bands and between the I2 and I3 bands. This classification as a water pixel is used as a complement to the ancillary land-water mask. Water pixels continue with fire detection processing to account for gas flares and other thermal anomalies. Here is an example of how the criteria for day versus night and for cloud identification can make a difference. On May 24, 2021, there were 7 points detected in the Yukon. The image on the left is the Dayland Cloud Fire RGB with plotted fire detections and a pop-up box showing the details of one of the points. The image on the right shows the VIIRS I4 3.74 micron image with the I1 0.64 micron overlaid on top. The I1 is a visible image which ends at the terminator, and a red circle shows the general location of the reported fire points. The location of these points beyond the terminator, where solar zenith angle is greater than 90 degrees, would mean that the algorithm would use the nighttime criteria for identifying clouds, looking for cold brightness temperatures in both the I5 and the I4. However, the I4 imagery shows that there are warm pixels suspiciously associated with a convective band of clouds. A close-up examination of the I4 3.74 micron shows the detected points were in a line of warm brightness temperatures just northeast of a band of convective clouds. A comparison with the I5 at 11.5 micron shows that these points are associated with cold brightness temperatures, which suggests that the points were actually cold cloud tops. Because these points were on the nighttime side of the terminator, there is no reflectance information in the I1, I2, or I3 bands. However, the day-night band image on the right, which senses visible light both day and night, has a bright line of clouds in the area of the fire detections. So this evidence confirms that the warm brightness temperatures in the I4 were the result of reflected solar energy from high clouds in the proximity of the terminator, which is less distinct during high latitude summers. The VIIRS Active Fire Detection criteria is not accounting for reflected solar energy from cloud tops at night. If false detections due to cloud reflectances at night are suspected, compare the I4 with the I5 and the day-night band. Another example from June the 25th, 2021, where fire points detected in an area designated as night were close to the terminator. This one was significant because two anomalous points were identified as fires and given names. The composite satellite image on the right shows where visible data stops at the terminator in the dotted yellow line. South of this line, the solar zenith angle is greater than 90 degrees and pixels are considered night. Red circles indicate the area where the heat points were detected. Considering the location of the detected heat points relative to the terminator and the fact that the clouds were present, these points merited further investigation. In the I4 3.74 micron band, you can see that warm pixels are adjacent to cold pixels that appear to be clouds. In the I5 11.5 band, it shows only cold pixels in the area of the warm pixels in the I4 image. This is a good indication that the warm pixels were associated with solar reflectance from cloud tops. Although no reflectance bands were available, the day-night band again shows bright reflectances in that area to confirm that the fire points were actually cloud tops. Since the DNB is highly sensitive in the visible radiation spectrum, it can often see the light from active large fires. Light from fires can be obscured by clouds and smoke, however, but smoke plumes that are visible in the day-night band can help to differentiate fires from city or other light sources. In this example, smoke plumes trail west and southwest from fires in Ontario and Manitoba, and not from the city lights further south. Also, as mentioned before, the day-night band can see reflected solar radiation at night from high cloud tops that are located near the terminator. Fire pixels are first identified with fixed threshold tests for strong radiometric signatures in either the I4 or the I5, which tend to be unequivocally associated with active fires or thermal anomalies. Note that saturated or fold-over pixels in the I4 are also considered in this criteria. Background fire pixels are fire pixels surrounding the candidate pixel. They need early identification so they can be excluded from later large window background and contextual tests. This avoids higher background averages by the inclusion of multiple fire pixels. They have slightly relaxed thresholds from the candidate fire pixels, and they will likely be identified as fires in later algorithm tests. There are two tests to filter out bright reflective targets during the day. One looks for pixels with solar reflection from bright surfaces such as sandbanks, ice, etc. that can be confused with active fires. The second test is for sun glint, which is associated with solar reflection from highly reflective surfaces such as water bodies, large metal rooftops, etc. This test considers reflectance thresholds, the satellite view angle, theta v, and the solar zenith angle, theta s. This test does not account for non-horizontal surfaces such as solar panels. In this 3.74 micron AVHRR pass on the left, hot brightness temperatures from sun glint over the ocean is fairly obvious, but reflected sunlight from small lakes can also appear as heat points at 3.7 micron. Those high brightness temperature points are shown here in the zoomed panel in the lower left part of the image. A comparison with the 0.63 micron visible image on the right shows that high brightness temperature points correspond with high reflectances from sun glint. Solar reflection from other satellites or aircraft can sometimes be misidentified as heat points. The circled area in the I4 3.74 micron image on the left shows a pixel much warmer than its surroundings, which lead to a false detection. This occurred at night when the solar zenith angle was greater than 90 degrees, so there were no reflectance bands available. However, the day-night band image on the right shows that this was caused by a high reflectance from some unknown source. The link at the bottom is to a blog by Curtis Seaman about these optical ghost features. Candidate fire pixels are selected using relatively liberal tests in order to include all potential pixels showing thermal anomalies on channel 4 or 3.74 micron. Daytime comparisons are made to median values in a 501 by 501 pixel window, excluding all pixels previously classified as cloud, water bodies, background fires, and non-zero quality flags. The contextual fire detection test in the active VIIRS algorithm uses a dynamic sampling window to characterize background conditions around each candidate fire pixel. The window can vary from 21 by 21 elements to 61 by 61 elements in the day or 71 by 71 elements at night until at least 25% or at least 10 valid pixels are encountered. Background fire pixels are not considered in this test. Here is an example of how the contextual tests would work. These isolated hot pixels at 3.74 micron occurred over land near the coast. Water pixels are excluded from the sampling window, but otherwise there are no clouds and only a couple of background fire pixels to ignore. Since the candidate fire pixels are considerably hotter than the surroundings in the square, they pass the contextual test and are assigned nominal confidence. At times, a detected heat point can seem suspicious when the thermal signal is weak and there are many other warm pixels from cloud reflectances in the area, as seen at 3.74 micron on the left. The dayland cloud fire RGB at the right shows the warm pixel in a faint red compared with the surroundings, which have no clouds in the vicinity. Imagery analysis supports the result of contextual tests, which ignored surrounding cloud pixels in the test window. The secondary tests in the algorithm are designed for less common pixel saturation or foldover scenarios and for potentially mischaracterized sun glint pixels. Noise in the input data may propagate through the algorithm, causing isolated false detections, mainly over oceans, so a persistence test is applied to the fire pixels over water. This test is not usually a factor in wildfire detection. Fire radiative power retrievals, or FRP, are done for each pixel identified as a fire. Due to frequent pixel saturation in the I4, or 3.74 micron, FRP retrievals use co-located M13 or 4.05 micron data following the equation from Wooster et al. In 2003. I4 band data is used to identify pixels and assist in the location of background pixels for the mean background radiance portion of the equation. M13 pixels coinciding with the fire affected and background pixels are used in the FRP retrieval. The resulting values are divided among coincident 3.75 meter fire pixels. There are fires the VIIRS Active Fires algorithm detects that aren't wildland fires, such as industrial burns, oil refineries, and volcanoes, but it can also be led astray by features that are not fires, such as solar farms and sun glint. Daytime solar reflectance from clouds adds to the total energy received at 3.74 micron, but it is usually accounted for in the active fires algorithm. These persistent anomalies will be flagged in a new CSPP version of the active fires software that will be available soon. The VIIRS Active Fires software has a very high detection success rate. However, there are infrequent times when the algorithm can be led astray. False detections can be caused by missed cloud classification, cloud top reflectances at night, mainly near the terminator, sun glint from water bodies and solar farms, solar reflections from objects such as other satellites and aircraft, and hot smoke plumes. Missed detections can be caused by fires obscured by clouds or smoke, fires obscured by terrain, fires that are too small or smoldering in the duff, fires in cloud or terrain shadows, and fires near the swath edge that have a larger pixel footprint and a greater chance for obscuration. To evaluate whether a fire point detected by the VIIRS Active Fire software is actually a wildland fire, find the fire pixel location in the I4 3.74 micron band imagery. Check how it compares with its surroundings. Are there nearby clouds which could be impacting the detection? Are there other fires in the area? Are there adjacent points anomalously cold, suggesting foldover from saturation? Are there persistent anomalies such as volcanoes, industrial sites, solar farms? Then examine the VIIRS I5 or 11.5 micron at the location of the fire pixel. See if it's also warm or if there are corresponding cold pixels from cloud tops. Are there clouds around the hot pixel, especially in areas designated as night? Comparisons are especially important at night when the RGB and visible imagery is not available. Finally, examine the VIIRS I1 0.64 micron band or dayland cloud fire RGB during the day or the day-night band at night. Check for clouds in the area of the hot pixels. Look for high reflectances such as cloud tops, sun glint, and solar farms. Check the DNB for light from large burning fires at night. Here is a list of links to online data sources for VIIRS active fire detections or other supporting fire imagery. Here is a list of references for more detailed information about the VIIRS Active Fires algorithm. That is the end of this lesson. However, I would like to acknowledge the important support from the individuals and agencies listed below that contributed to this training and to the satellite tools used in the detection and monitoring of wildland fires. Thank you for watching this training module.